Yes, it is. Okay. So let's now have a look at the exponentials part of it. And start off by, let's have a look at what the function actually looks like, the basic exponential. And you may remember when we looked at the logs, I talked about how it was the inverse of an exponential curve, and the exponential is the inverse of the log curve. So basically it's the same graph, just turned on its side. Or actually more appropriately, turned 45 degrees. It's actually a reflection in the line y equals x. So it is the log curve, but reflected in the line y equals x. So instead of having an x-intercept of 1, it has a y-intercept of 1. This is, of course, when the base is greater than 1. If the base was less than 1, then it would be reflected in the y-axis. So, or when I say less than 1, between 0 and 1, we don't have negative bases, same as we don't have negative bases in logs. Of course, if I use negative indices, then the red one would become a to the power of negative x, but now the base would be between 0 and 1. And the blue one would be a to the negative x, but now the base is bigger than 1, because of course that negative in the power goes 1 over. So they are the same graphs, but they could have different equations depending on the base. The most common one that we see would be that red one. That's pretty much the standard one we look at. Domain, well, we can see from our graph there's no breaks in it. It's a nice continuous graph, or real x. And the range is y is greater than 0. So that is like the opposite as well as the log curve. You remember the log curve, the domain was x is greater than 0, but the range was all real y. So the sort of the x and y's have swapped around. Y equals e to the x is a really important function that we're going to focus on in this work. E is what we call an irrational number. Much like pi, it goes on forever and ever and ever and doesn't repeat. And, well, obviously we don't know the last number, but I can tell you that the 1,729th decimal place is 0. Okay. So, yeah, and just in case you wanted to know that. Its definition, its formal definition is this. It's 1 plus 1 over n to the power of n, but as n gets bigger and bigger and bigger, and so approaches infinity, we'll come to the exact value of e. So if you were to plug in, obviously, 1 plus 1 over 1 to the power of 1, you just get 2, and that's a pretty lousy approximation. Sub 2 in, you get 1.5 squared, which is 2.25? Yeah. So it's getting closer and closer. So as n increases, we get closer. The approximation that you get on your calculator, limited, of course, because of the screen, 2.718281828. It actually looks like it's repeating, but that's just obviously because of, that's how big your screen is. If your screen was bigger, you'd then see that pattern disappears and other numerals start coming into it. So e cubed, on your calculators, obviously, you'd use the same button as the natural logarithm button, but above it, you'll probably see a notation e to the power of x or something like that. So you'd probably have to hit shift or second function, depending on what it is on your calculator, and then cube, and you could work out e cubed. But we're interested in our function e to the x. How do we differentiate it? How do we integrate it? Well, let's have a look at differentiating first of all. It's an amazing function. It is the only function that is its own derivative. So if you want to differentiate e to the function x, you get the derivative, but it's still times e to the function x. The power does not change. So when I say it's its own function, that's when I'm talking about the most basic of them all, e to the power of x, because if you think about that, if you differentiate the power is x, differentiate x, you get 1 times in e to the x, which is e to the x. So it is its own derivative. What does that mean? Graphically, it means on y equals e to the x that the y value will always be the same as the slope of the curve at that point if you were to draw a tangent in. Remember, the derivative measures the slope at a particular point. Now, if the base is not e, it's okay. We still do it the same, but we multiply it by the natural log of the base. I hopefully recall when we looked at logarithms, we're talking about base e, but we said if the base wasn't e with logarithms, that's okay, we did it the same, but we divided by the natural log of the base. So with exponentials, we multiply by the natural log of the base. So that's why with e the function x, we don't have it there, because remember log e, natural log of e is 1. So there it is. There's a question that you hope you're going to get in the test. Why? Because e to the x differentiated. Oh, it's e to the x. There you go. E to the 5x. Well, now it's going to be slightly different, because if we differentiate 5x, we're going to get 5. So now we just place 5 out the front, and we have 5e to the 5x. Does 4x plus 3, again differentiate, we get 4, place that out the front, 4e to the 4x. So a very simple function to differentiate, depending of course on what the power is. Because you don't have to have a linear function, you could have a quadratic. Not that that's a big hassle to differentiate either. Differentiate x squared plus 3x plus 2, we get 2x plus 3, so it's 2x plus 3 times e to the etc, etc, etc. Product rule. Okay, let's get those brain cells working. It's been a few weeks. So we have to write down the first, diff the second. So write down the first 3x squared, differentiate the second bit. Well, e to the 4x, power is 4x, differentiate 4x, we get 4. So it's 4e to the 4x, plus write down the second e to the 4x times differentiate the first, differentiate 3x squared, we get 6x. So pulling out, well actually I tied it up first before I factorised, but you'll see there's a common factor of 6x in there, also a common factor of e to the 4x. So 6x, e to the 4x, 2x plus 1. The chain rule, or as I like to call it, anarchy, bring down the power. Okay, bring that power down, 7. Lower the power is 6. And remember, we always have to differentiate the inside of the parentheses. So inside the parentheses, we have e to the 3x plus 2, which is 3e to the 3x. Tidying that one up, 21e to the 3x, e to the 3x plus 2 to the power of 6. Quotient rule. Okay, so how we go with remembering that one. Square the bottom, write down the bottom, diff the top, minus write down the top, diff the bottom. So square the bottom, that's the easy bit, place parentheses around it, square. Okay, write down the bottom, diff the top, oh, the top's easy, e to the x. Differentiate e to the x, we get e to the x. Minus, write down the top, e to the x. Differentiate the bottom, oh, again, that's easy, e to the x is e to the x. Where you've got to be very, very careful, of course, is remember your index laws. It's so easy to make a silly mistake when expanding the top out. E to the x times e to the x is not e to the x squared. It is, of course, e to the 2x. We add the powers. So just make sure, take a bit of care there, because that is a classic silly mistake that can be made when people are working too quick. So the e to the 2x's end up cancelling, and we just have 3e to the power of x on e to the x plus 3, all squared. Well, this is one of the original reasons we started using calculus, was to find the equations of tangents. So let's put it into a practical question. The y value is a bit strange because it's e squared plus 1. I've left it as an exact value. So it's the point 1, e squared plus 1, but that doesn't change the rules. I want to find the equation of a tangent. Tangent's a line. Equation of a line, I need a point, I need a slope. I've got a point, I need a slope. Oh, that's all right, I can find the slope using 2 points. Ah, I only got 1 point, damn. Ah, that's why we use calculus, okay. So let's differentiate. E to the 2x plus 1, we differentiate it, 2e to the 2x. But that, of course, is not the slope of the tangent. Again, another classic mistake, especially when working with exponentials, is to leave that as 2e to the 2x. Morning. So that's just the formula to work out the slope. We've got to sub in the actual x value to find the slope. And so it's 2e squared. All right, it's a little bit different to just our classic coordinate geometry where we've got numbers, but again, the rules are the same. So y minus the y value, which is e squared plus 1, equals the slope 2e squared times x minus the x value. Well, that was just 1. Expanding that out, I've put it in general form, so I've put everything to the left-hand side, and we've got this rather strange-looking equation of a line. But it is the equation of a line because remember, e is just an irrational number. So we do have some multiple times x, some multiple times y, and then just some constant number. It just looks strange, but it is an equation of a straight line. All right, here's one where the base is not e, but we said that's not a problem. We'll just do it the same, but multiply by the natural log of the base, so log 4 in this case. Use of parentheses here is really important too, because if I didn't put parentheses there, it could look like log of 44 to the power of x squared and so on. So make sure it's very clear what your answer is. Y equals log x. Hang on, why am I asking this in exponentials? Well, all right, let's think back. Differentiate logs. Derivative over function. So that is, hang on, I'm going to do it a different way now. X is equal to e to the power of y. If y is log x, x is equal to e to the power of y. I now know that if I differentiate x with respect to y, I'll get e to the power of y. But that's dx to y. I want dy dx. Dy dx is 1 over e to the power of y. But hang on, e to the power of y, that's x, and there's our derivative, 1 over x. Now, I'm not suggesting that you would differentiate log x that way. I mean, obviously, it's 1 over x. But it's a lovely way of showing you why, when you differentiate the log, you get derivative on function. Because it's actually via the exponential function and the fact that it is its own derivative, and that's where it all comes from. All righty, welcome back.